Yes, Shane said in my introduction, I am the current president of UAIS. We are a student group on the University of Alberta campus, whose main goal is to bring different AI technologies, uh, all the knowledge down to more of an undergraduate level, because currently it's still very much a graduate level study. And yes, thank you for linking to the website. Uh, and just to give a background of myself, I am a third year computing science major, specialization. So I don't have a minor in medicine. I don't know that much about medicine myself. So hopefully the examples themselves are good enough. Shane did help quite a bit with the examples stuff, but I'll be covering a lot of the technical, more generalized aspects of it, but still given some of the medical examples. All right. So for what I'm going to go over today, essentially, I'm going to be splitting this into 4 parts, or almost could be split really into 3 parts. So we're going to cover convolutional neural networks, recurrent neural networks, NLP, natural language processing, and reinforcement learning. The reason I said kind of 3 because natural language processing kind of goes hand in hand a lot of the time with recurrent neural networks. All right. So CNN, a convolutional neural network. So what is that? It's a very specific architecture you're going to use when you're making like big, deep neural networks. You're usually going to use this for data such as like images, audio, or other sort of 2D data. And when I say 2D data, you can actually generalize this to higher dimensions. So you can do this to like 3D scans and stuff like that. So the main applications of this, right? Where can you see this in the medical field? You can see this in like radiology, where you're taking medical images. You can see this in pathology when you're trying to, you're studying organs and different things. You can also see it in dermatology because you're dealing with skin, and a lot of times you can take pictures of skin, right? So you can think of this, right? If you can represent this as some sort of image, right, you can then usually use convolutional neural networks. And just to also kind of follow on the terminology example, for the symposium, actually, we had a booth and we present a notebook where we actually have a model that can actually properly detect whether a certain photo the person has actually a malignant skin cancer, right? And we get to an accuracy of something like 95 or 96%, which is actually higher than general doctors, right? And that's why it can be really powerful, is because with enough training, you can get very high levels of accuracy that can actually outperform humans, right? It could outperform experts, right, who have spent years studying this. And why do we use this sort of data? Like, why is it so powerful? Why can't we just use a regular neural network? Because a convolutional neural network is data shift invariant. Now, what exactly does this mean? Um, if you see me right now, like if you take like a screenshot of my video right now as a frame, and then you take a couple minutes later, just a couple seconds, like right now, you probably notice I moved very slightly, right? Very slightly. You may not even notice that what before I pointed it out, right? Because to you, it's essentially the same thing, right? To your brain, it's essentially the same thing, right? It's still a picture of me with a Minecraft background. I'm not really doing anything there. I'm wearing the same clothes, same everything. But to a computer who just sees this in terms of numbers, if you pass this to a regular neural network where all the previous weights are densely connected to all the next weights, to all the nodes in the next layers, there is a huge difference, right? Even if all the data is essentially the same, but just slightly shifted in place, it affects it very differently. And so regular neural networks have a harder time generalizing when they're trying to see images than they have seen before, but are just in a slightly different place than before. And this happens in the real world all the time because you can't align things perfectly, right? Sometimes the scale might be different, the rotation might be different, right? If you're taking X-rays, right, it's not always going to be the same positioning. But as humans, we kind of filter that out, and we still kind of recognize as certain stuff as the same thing. And so that is essentially why it's powerful. Also, the fact that everything is not going to be fully connected uh, obviously helps with the data shift invariance, right? It doesn't get as affected when your data shifts, but also has a nice bonus that's also going to reduce the number of weights, which can also help increase your computation time. And so here would be an example, right? If you're passing this through a convolutional neural network, right, it will look at a subsection of the image, and then it'll pass it through the convolutional layer, and then you can repeat this multiple times, right? So then that each time of those convolutional layers, it can perform a convolution again and pass it on to another layer, and so on until you get a final output. In this case, you know, you may be trying to predict whether the person's having a migraine or not. And here I'm going to go a little bit into the math. Hopefully, you're not too scared off by the math. But in this example, right, you have this grid or this matrix, this image of numbers. They're all ranged from 0 to 4. And then you're going to apply something called a filter or a kernel. And then you're going to get a new output image, right? And that's essentially the convolutional process. And you'll iterate through each subset, right? Through each subset of the image. You'll apply the kernel or the filter at each subset to get a new pixel value, and that will create a new output image. And this is essentially the same technology. What do you mean by convolutional not being fully connected? So probably should have had an image of a normal neural network. So I'll just actually quickly Google it. If you look at neural network, you look at an image here, you'll notice that actually, let's choose this one. There's a little bit more connections. You'll notice that everything from each neuron, you could say, for each node onto the next layer, you see there's an arrow coming from each one to the next layer. And from the layer, you can see that's an arrow coming from each previous node. In a convolutional neural network, they won't all be connected to each other in the next layer. It'll be a sparse connection, right? Only a handful will be connected, right? So like in this image, let's say in this first hidden layer, you'll only have a connection coming from like the X1 and X2. And then the second one, you'll have one coming from like X2 and X3. And then the next one, you'll have like from X3 and X4, right? So they're not fully connected. And if you use something like TensorFlow Keras, a regular layer would be actually called a dense layer. So that's where that comes from. Go back in the slides. I'll go my speaker notes. Oh man, probably shouldn't have exited full screen. All right. That's fine. So that's what happens, right? Now I'll go over a quick math example. What is this, this mathematical formula, right? You take this subset, right? And this is highlighted in the cyan of either this 2, 3, 4, 5, 2, 2, 4, 3, 3, 2, 2, 2, 1, 1. And you apply this filter to get this output image. And I don't know if I mentioned it earlier, but this is the same process that you use like in Instagram, right? When you take a photo and then you apply a filter, it's using a filter or a kernel, which is this other matrix that it applies a convolution on. And depending what values you use on that filter, you can get very different effects out of it, right? So you can get like not every single image, not a single filter is going to have like a black and white filter is going to do something slightly easier. But if you want an edge detection, for example, very easy common way is to use a very specific convolution filter that has values such that the output image will actually produce like only really the edges of whatever subject you're trying to get the edges of. But anyways, this subset, right, we take it, we apply this convolution, and we're going to get some final value. And now what numbers is going to be. As you can see in these other ones, right, these are all the other numbers. And although the first initial numbers in this bigger original image are just random numbers that I put in manually, these final numbers are the actual mathematical values that you're going to get if you apply convolution. And so what is this convolution process? So you take the subset that you want to convolute, And then you apply the filter here to get the final output value. And what is that? If you think of it in terms of like linear algebra, you can think of these as matrices. And so what you would do is you would flatten the matrices and then do your dot product to get a singular final product. You wouldn't. So it's not like a matrix multiplication, right? You can see that here, where I have it like written all in long, but essentially, right? You take, for example, in the first subset right here, 2 times the 1, the 4 times the 2, the 3 times the 1, the 3 times the 2, and so on. You get the product of each, you sum them up, and then you get a final value, which in this case is a 32. So you know for that subset, with that specific filter, you get a final value, which is a 32. A question that may come up is, well, what filter are we going to use? And it'll very much depend on the task that you're performing, right? What are you trying to get out of it? If you're using something like TensorFlow Keras, I believe it already chooses the numbers for you. All you need to specify is the shape of your filter, right? In this case, it's a 3x3 filter, but you could have like a 4x5 if you wanted to. And the values you get, it gets from some statistical number distribution. I don't remember what the distribution is, but it's not too important when you're for a lot of those other tasks. But if you're doing something where like the edges might matter, then you might want to use a very specific filter that can detect the edges. Another thing that happens is strides. So I mentioned that you take a subset and then you go on to the next element. And how do you decide what the next element is going to be? Well, you kind of decided with strides. In the previous example, you had a stride of 1 and 1, because assume that once you get this first like subsection, you just move on to the next elements, right? Just by 1. If you jump by 1, then you get to the end and you start over again from the original position down by 1, and then you go on by 1, right? You jump by 1. And that's your stride. You can change this, right? You don't have to leave it at 1. You can change this to be like 2, right? So instead of getting like a subsection of images and then jumping onto the next one, it'll skip that one and then jump again, and then it'll take that subsection and do the convolution. So what may be some advantages of doing this? One of the advantages is that you can downsample your image furthermore, right? If you have a really big image to start out with, you can downsample it more and you can generalize your image a little bit more, which can help a lot with your training time, right? You can get faster training potentially. Oh, and I guess one more thing is there's also padding. Most of the time, I personally don't really use it because I don't, when I'm working with certain models, it doesn't really seem to affect it. But padding essentially is adding extra values onto the original image such that your output image keeps the same dimensions, right? If you notice all these examples of all these convolutions, you'll notice that the original image is slightly bigger than the final image, right? The final image is only very slightly smaller. And that happens because when you get to the end of the image, right, you can't go further because there's no other values to go with, right? So what padding does is it will take the image and pad like zeros all around. So you have like a bigger original image. So you can apply the convolution. And then in your final image will actually end up having the same number of dimensions. Something like if you're doing social media application where you're doing these filters like Instagram, again, you might want to keep the same dimension. So you might want to use some padding. But if you're using machine learning, a lot of the times padding won't matter. If you have a really small image to begin with, then you probably don't want to downsample it too fast if you want to make it a bunch of deep layers. So it will very much depend on the application. But long story short, right? Convolution, you take a filter, you apply to a subsection. The strides decide by how much you jump onto the next subsection of elements. And in the end, you get this output image, which will contain some more generalized information about the image. And it will be a more compact representation. A second process that might happen right after you do some convolution is called pooling. A lot of times you use something like max pooling, but there's like minimum pooling and average pooling. What that does is it's still the same general process where you take a subsection, but instead of applying convolution, you apply pooling. And what does that mean? Is that essentially you look at all the values that you currently have in the subsection and you choose some output value based on some mathematical equation, right? So you only take one number from all those original numbers. There's no external like filter or kernel that you apply onto this, right? So an average, it would be you take all the elements and you take the average. Max pooling, it's essentially taking all the sub elements and then taking the greatest value, right? So in this, if you take this bottom right corner, 39, 36, 31, and question mark. Oh, sorry. That was from the previous number, which was a 32. So remember here, there was a 32, right? This will get mapped to some final value over here. And what would that value be? All right, no answers in the chat. All right, that's okay. Oh, there you go. 39. Yes, it will be 39 because, right? Because we're doing max pooling of a 2 by 2. You take this element 2 by 2, the biggest number will be a 39. And the reason you may use this is, again, it really helps with downsampling and it helps generalize the image even more. And you can kind of think of it as if you kind of zoomed out of an image, right? You just kind of made it smaller, but a lot of the general information, a lot of the main pixels are kind of still there, right? The most prominent important ones are still there. And that's the goal of pooling, is to just downsampling the image even more, because the smaller you can get that image, but still containing as much information as possible, the faster the other computation can happen, right? Because matrix multiplications are computationally expensive. So the less your original image before it passes through the rest of the system is, the smaller it is, the faster the computation will be. All right. So that was convolutional neural networks. So before I move on to RNNs, does anybody have any outstanding questions? All right. Got one no, that's good enough for me. All right, so recurrent neural networks. What are they used in? Right, I'm going to be on first of all, what are you going to use them in before we go into how they work? So they're going to use in time series data. Now, what is time series data? That's where you have essentially like a list of data, but the order matters, right? The order is very important to the context of the data. And there's a myriad of real world scenarios where this happens. For speech, for example, right? Right now I'm talking, I'm forming sentences. When I ask you maybe, how are you doing? Right? The order in which I say those words convey a very specific meaning, right? If I say, I am happy, right? That means I'm telling you that I am happy. If I change the order of those words and I say, am I happy? All of a sudden the meaning is changed. I'm no longer telling you that I'm happy. I'm asking you if I'm happy. And the order very much matters. In videos, right? The order very much matters, right? Because you have all these frames. If all the frames of each, right, of the video were out of order, the video wouldn't really make sense anymore. So it happens a lot in real world, right? Just anything that goes through time, really. That's why it's called time series, right? Where the past matters in terms of context for your current state. You're going to use recurrent neural network. So what are some medical applications, right? Obviously, video and speech can, it's a very general topic. So obviously they can apply into recurrent networks. But in terms of very more specific medical situations, you'll have something like diagnosing symptoms or predicting a disease progression. If a person has a certain disease, right, two diseases could potentially have like very similar symptoms, but the order that they appear can be different, or the time span in between in which they occur can also be different, right? So you can still have essentially the same data, but the order affects your final conclusion of what their disease might be. Is there any data in which time series does not matter? If you're taking still images, right, of somebody, right, in those cases, right, when you see the image of like one leg versus the other, where you're seeing very different things, it won't really matter. If, for example, you're solving you're making a house prediction model, uh, you may not really have previous data, right? Or actually, a better example would be if you're analyzing the brain. If you want to see something that's happening at the brain at a very specific point in time, where the previous state of the brain doesn't matter, then you can still have like different timestamps of the brain, but what you're trying to analyze, it doesn't really rely on the past. So in that scenario, right, it may not matter. And that could be like if you're trying to see what level of arousal the brain is having, right? If you show a patient a certain image and you're trying to see what level of arousal they have, you're still going to be taking multiple, snapshots of their brain at a moment in time. But what it was previously won't really matter for what it's going to be next necessarily. But if you're trying to see how well they're doing over time, then it very much matters how they were doing a second previously compared to how they're doing now. And so forecasting, right, is something that happens. And I also said recording EEG, right? Because a lot of the times it will matter. So a lot of times when you're recording EEG, recurrent neural networks, they will appear. Forecasting, right? And forecasting happens not just in the medical application, right? They can happen in stuff like stock markets, right? If you're trying to forecast a specific stock. But in the medical field, right, it can notes. All right. So this is taken from a presentation our another executive for the club did for another club actually. But this is kind of a very high level example, right? Well, I think this was a snapshot of the EEG data of a specific individual who was seeing images and then recording like their certain levels of their brain. Right, but you have these numerical values that are different spots in the brain, right? They get mapped through this neural network and then they produce some certain output, right? And then what we do is you take that output and then you pass it back through the initial input layer as a previous prediction. And now that you give it new data, right? This new data is not only include obviously the new data, but it's also going to include the past prediction, right? How was it previously? And then that past prediction now gets passed on through the network. So you have like this loop, right, where it feeds back into itself again. A more specific mathematical representation of this is, right, you have this recurrent neuron, right, where it has a value, right, has an output, and an output goes back into its input, right, into the next state, right? And that way it can essentially remember what's happening. So I have a little equation like s at the time t is going to equal to some function of s at the time t minus 1, so the previous time step. And then the theta there is just an activation function. That just comes in more into where you do networks with activation functions, but not really as important. But essentially, right, you're having this equation where your previous state, you're going to use this to your current state, right? And then it can also help think of this in terms of if you unfolded this, right? If you follow through this equation and you unfold it a bit more, right? Now s of t, now that's a function of s of t minus 1, which is in itself a function of s t minus 2. And we think of this visually. Let's see if I have this. You have the state passes on to this other state, right, to the current state, and the current state will pass this current state onto the future state, and so on. So you can see a connection of your previous state passing on its data to its next state. And then now we'll enter in something external signals, because so far we're just passing on our previous states, right? In the first example I gave, I'm also giving current information, right? Because that very much matters. And so that's what's going to be this X. And here I'm still showing it into an unfolded example, but then you can fold it back to have something simpler. But right, you'll have this previous state, right? So your current state, right, your state at time t will equal a function of your previous state, right, t minus 1, with a current input, right? Because it's not x t minus 1, it's x of t. right? And then your activation function, and you pass that through a function, and then it'll produce a value, right? If you unfold it a little bit more, right, it's a function of a function, and then that function will contain something like s of t minus 2 of x of t minus 1, and then here I forgot it, but there would be of an x t still. But the visual aspect, there's no error there. Or you're getting these inputs, right? So you can think of it as a sentence, right? If I'm translating something, right, and I give you only one word, that may mean something. But as soon as I add in the second word, right, with the context of the first word, the translation might change, right? What I'm telling you might actually change. And so that's where you see this actually being useful, right? It's because sure, you get like in the first couple of predictions where it doesn't have all the data in yet, right? It might predict something, but as soon as you add different data in a specific order, right, you'll see its prediction change in real time. And you can try this with GPT-3, which is a very big language model. But I'll touch on it maybe a little bit more when we get to NLP. So we in this example I gave, right, with this very basic structure, we actually do have a small problem, right, which is that we can only really look a one-time step back, and sometimes we want to look a little bit further back, right, because we might get inaccurate results. Something else that happens with these activation functions, right, these theta functions, is that you'll very quickly you'll start forgetting the past, right, very quickly. Like the thing you saw maybe like 2 time steps ago is not worth all that much, right? It may only be like only 10% of what you remember, right? So very quickly you start forgetting things. And again, with these activation functions, you get something like a vanishing gradient, or the opposite, which is an exploding gradient. So how do we solve this problem? We use a subset of a recurrent neural network, which is called long short-term memory. And here I give an example of a sentence to try to make it as easy to understand, right? I have a sentence called, "My new shirt, which I received as a prize for an online contest, was too big," right? And here I have an underlined shirt and too big. When I'm saying too big, right, what am I referring to, right? You as an English speaker, you'll know that when I'm saying what was too big, well, that was the shirt, the new shirt I got. To if you have this very basic structure that I showed you previously, you know, the model may have already forgotten about the shirt, right? Because with all these other new words that it received, it already started forgetting about the previous ones. And so having a long short-term memory may help with that.
You don't lean or you should be fine. Just to make sure you don't.
Say again? Oh, all right. So in this, right, we'll have like these subset of neural networks, right? And we'll pass them through different gates, right? So this first neural network, right, we'll pass it through a selection gate, whether we want to select it. Another one where we want to forget it, because some of the words in this phrase don't really matter into the overall context, right? The A here probably won't really matter. If I remove this from the sentence, you'll probably still understand that I meant that the shirt was from I got it from as a prize. The A part here probably doesn't really matter that much. So sometimes you may want to forget some stuff, right? Because it won't really match your memory. Or you might want to ignore it, right? And so what these different gates do, right, is that you can essentially remember some certain piece of information more than others. So you can can kind of rank them in terms of importance. Now, I don't want to go into much more detail, like much more of the mathematics of this, because it is very hard to get it at first glance, and it can be very confusing. So I won't. But essentially, think of it now is we still have those same structures, right? Where the previous data may affect it, but now we pass it through different gates. So a certain prediction at a certain time step, right? Do we want to pass it on to the future prediction? Yes, no, to what importance? And that's what those gates will control. How can this model be used in a real world aspect, right? This is more of a translation sort of thing. So that's how you would use it in that sense. But if I go into one of the previous examples, which was, let's say we're doing the forecasting of hospital bed occupancy. Right? You may like, let's say you get like a steady rate. Let's say you always like something like around like 30% occupancy of your hospital beds in a specific ward, right? Like 30%. Like it'll fluctuate a little bit, like 25, 35. Sometimes it'll get to the 40s, right? But there was a big accident right in a hospital, like a building collapsed, right? All of a sudden you got a huge surge, right? And now you've basically filled all the beds in that ward. It's like 100%. But luckily, the injuries weren't that bad, and like a week later or so, most people will have gone out of the hospital. They've gotten better. They're no longer in the ward, right? So you've got that big spike. Do you want your neural network to really remember that spike, and then when it's trying to predict what its occupancy is going to be next, to like, okay, well, maybe it might jump to 80% next week? You probably don't, right? You may want to recognize that it's a temporary spike, and you may want it to ignore that spike. Hopefully, all right. And before I move on, a couple more things is that long short-term memory cells allow context-dependent accumulation forgetting, right? So here the context will also determine whether you want to remember something or forget it. And this helps, right, in really remembering the past and being able to apply it to the present. The network compromise, right, of prediction, a selection, of ignoring and forgetting sub-networks, right? So you have these smaller sub-networks that all work independently of each other, and they pass through these gates. All right. NLP, natural language processing. So this is a field, and a lot of times you'll be using these models that we just talked about, like long short-term memory. But NLP is natural language processing. What is that? It's essentially the question of how do we make computers understand language. Normally, when you're given a computer instructions, you will write code, right, and then pass through a compiler, which essentially will spit out ones and zeros that the computer can actually understand, that the CPU can actually execute. But as humans, we don't really talk like that. We don't really talk in terms of mathematical equations, right? Maybe if you're a mathematician, you might, but most regular people, I'll include myself in there. We talk normally, right? We don't talk in terms of ones and zeros. So that creates a challenge, right? Where you have humans who talk at this very high level abstract method, and then computers who are very precise and binary in terms of the way that they talk. So natural language processing, it's a whole field of trying to essentially kind of translate that in a way, right? Trying to make a computer understand natural speech. And that's why the natural part is very important, right? Because if it's just language processing, then okay, then this would just be like a Python course, or like a specific programming language course, right? Where, okay, we'll just program everything you want to this very specific language. But we want natural language, right? We want to understand English or Spanish or French. And there's a lot of applications, right? In terms of general applications, right? Google Translate. When you're using Google Translate, that is very much natural language processing. It's not just some human translator who's translating your phrases in real time. It's a computer who's actually doing that. And the computer is not just going word for word and then looking up into some big dictionary where it can try, okay, I know this word dog in Spanish is going to translate into perro. So, okay, I know that dog means perro. So if I'm saying I have a dog, and in Spanish, I'll translate yo tengo perro, or yo tengo un perro, right? Actually, that example is horrible because that one actually can literally translate it word for word. But if you have more complicated sentences, right, the ordering might change, right? If you have an adjective on a word, right, your adjective on that specific word may happen beforehand in one language, but in another language, it may happen afterwards. If I say I have a beautiful dog, the beautiful comes before dog, but in Spanish, the beautiful will come after dog, right? I'll say I have un perro bonito, right? Dog beautiful. In terms of medical applications, right? Analyzing EMRs, there's electronic medical records, genomic data, right? So genes. also have like virtual doctors and health assistants, right? All of these, you really have to essentially communicate with somebody. Well, maybe not genome, but you know with the virtual doctors, this health assistants, you have to communicate with somebody. So the person needs to be able to tell the computer something, and the computer has to be able to actually analyze it and produce something meaningful. Genomic data. Why does that count as natural language processing? Is that you can kind of think of genome as a sentence, right? Where you have these very specific, I don't remember the technical term, but the little, the little sticks in your DNA. Somebody could probably quickly type it, the proper medical term for that. But those chemicals are base pairs. Thank you. So you have these base pairs. The order very much matters, right? The order in which you have this can determine whether you're perfectly fine or you have some preconditioning genetic condition. So even though it's not quite a language, you can very much apply the same processes to that sort of data, because it ends up, you can essentially still count that as the same thing. Oh, and I also I didn't link it into the slide itself, but there's like, for example, companies like Babylon Health who make a lot of products that use natural language processing, like health assistants, right? Like kind of like a Siri for your health, where it can be like, hey Siri, this is what I'm feeling. Please tell me how I'm doing. And I'm assuming their product doesn't just go on WebMD and tell you have cancer. I'm assuming it probably gives you like probably better information, but the process that it would use would be natural language processing. And how am I going to use this? How am I actually going to process? It's a very big field. There's a lot of very like smaller subsets into all sorts of things you can do. In terms of neural networks, which is what you use, you'll probably use the recurrent neural networks that I mentioned previously. But because it's a very wide field, I'm not going to go into very concrete mathematical examples. But does anybody have any questions about natural language processing? All right. And now finally, reinforcement learning. So what is that? It's kind of like training a computer, but if it were a dog. And for the first example, I will very much be going over like how you train an example. So just as a smaller recap, when you talk about machine learning, you usually have like three big subsets of that. You'll have, in terms of like technologies you may use, right, or algorithms. You'll have your supervised learning, which is you have labeled data. So you have data and you know what you want to kind of get as the label value, and you essentially want to be able to repeat that with new unseen data. You have unsupervised learning where you have unlabeled data. So you still have all that data, but you still may want to get something out of it. Like you may use clustering, right? To say, okay, well, I don't know what exactly this image may have, but I know it's going to be this specific image is going to be very similar to all these other types of images. So let's say if you had a music recommendation engine, that could be something like it I have, right? It doesn't necessarily need to know what the song is, right? But it knows, okay, this song is very similar to all these other songs, so I may recommend this song to people who listen to these other songs. But then you have reinforcement learning, which isn't quite like the other two. The main thing that makes it different is that now it's not just a model that just kind of sits there and you give some input and just spits out a value. Now you have a model who's more so like an agent, and it's actually interacting in an environment, and it's taking actions, and then it's seeing how well it does, and then it reperforms the action over and over again, either forever or until it reaches like a terminal state, right, where it reaches its final goal. So you don't teach it by telling it necessarily what you want, right? So you may not tell it, okay, when you do this, I want you to do this. You'll actually just tell it, when it takes a certain action, you'll tell it, okay, this is how good your action was. All right, I'll give you like a +1 or a -1, right? You'll give it some sort of reward. And the goal of that agent is to maximize the sum of its rewards in the long term. And we humans do a lot of this, right? Where you may want to think of in terms of long term, in terms of your gains, right? That's possibly why you went to school, right? Because right now you're at school, you're maybe not making as much money, you're probably losing money because you have to pay for school. And so it doesn't make a lot of sense. But in the long term, it makes sense, right? Because overall, then afterwards, you'll have a more, you'll do a field that you like, you'll be making more money, right? You're maximizing the sum of your rewards over the long term. Uh, and so, some real world applications of this, in terms of non-medical, there's self-driving cars. Self-driving cars, think about it, right? At every time step that the car is driving, it needs to perform an action of some sort, and that action will lead it to some new state, right? It may have moved into a different location, right? Maybe different latitude or longitude, right? Maybe further down the road, it's going to be in this new state. And then in this new state, it then needs to take an action again until it reaches a terminal state. And for a self-driving car, would essentially be two terminal states. Either it crashes, hopefully it doesn't, but that is one very real possibility. Either it crashes or it reaches its final destination, right? You want it to go to U of A campus, right? That was your end goal. You got there. That's your terminal state. And then it can see, okay, I did well here. I didn't do so well here. Maybe I sped across the speed zone and I got a ticket, right? You might want to punish it for that, right? Be like, okay, you didn't do that well here. Yes, you got me there fast. You got me there in time, but you got me a ticket. So, I'll give you a lower reward. Or let's say parked really well. You parked between the lines, the perfect parking anybody could ever do, but it was like near a fire hydrant. Or it parked somewhere where you didn't have the permit to pass, and all of a sudden you got a ticket. Again, you may want to punish it. In terms of a medical aspect, you can have this in terms of a surgical robot, where the surgery, it may be performing a surgery, and if it makes some sort of mistake, right, you may want to give it a negative reward. And if it finishes the surgery perfectly, you want to give it some positive reward. With computers, it'll very much just be a number. It'll be some numerical output, right? Like a +1 or -1, a +100, -100, and so on. And now for the dog example, because I really like the dog example. So I got a puppy last weekend. And at the end of the slides, I'll have a couple of pictures. So if you stick around, there will be a reward for you, right? But right now we're trying to potty train him. And it's quite a process, right? It has peed quite a bit of times inside the house. I think it's even pooped at one time. I wasn't there, fortunately, so I didn't have to pick it up. But he has peed and pooped inside the house, and we don't like that, right? We're trying to encourage him not to do that. So what we do, right, is anytime we notice about to pee, we take him outside, and then he pees, and then we give him a reward, which will be a treat, a belly rub, and then maybe a couple of kisses, right, to instill in itself, right, over time it'll learn, okay, if I want to get treats and all this love and attention, I should be peeing and pooping outside, not inside, because when I'm inside, they don't do anything for me, right? And that's its negative reward, right? The nice thing about robots and computers is they don't have any ethical rights, so you can pretty much give them as many -100 as you want. With real life creatures, you obviously can't do that, because then you get to the territory of animal abuse very quickly. All right, so if it's a dog, right, I can't just hit it, right, if it does something wrong. Not yet, anyway. Yeah, yeah, until they take over, that is. But I can't hit the dog, right? But I can just not give it any treat. And if you've had dogs where you've gone through the potty training phase and you've done it like that, you'll notice that is actually still effect. You can still end up training him without giving him negative rewards, because the goal of the agent is to maximize some of the rewards. It doesn't want to necessarily reach a reward of a specific value. It just wants to make sure that that value that it's getting, it's going to be the biggest that it can get. And so that's why it doesn't matter that much necessarily sometimes in terms of values that you give it, as long as what the general action that you want it to take are still higher ranked than the others. So over time, it'll prefer those actions over other actions. In terms of surgical robot example, how long would it usually take for the machine to almost perfect the algorithm? That'll very much depend, and something that you can actually do there to speed up. Because if you're in the real world, you have to have you have to prepare whatever it's going to perform surgery on, right? And then it also has to take its time. It can only move so fast as it can mechanically move and safely move. So it might take a lot of time, right? There's a lot of trial and error, right? And so some things you can do to speed it up is you can use, so that's online training, right? So we're training in real time in the real world. You can something called offline training where you still like you simulate all the environment, right? Where it's simulating a surgery, but it's all hypothetical. Nothing's happening in the real world. And when you do that, you can speed up the training time because all of a sudden it can train multiple times per second, right, across multiple like hundreds of computers all at the same time with all the computational power you can afford, and it'll perform much faster. But in terms of how much time it'll take, uh, generally speaking, the more complicated the task you're trying to get it to do is, the more time it'll take for it to learn, right? The bigger your state space, so how big your environment can change, how much it can change your state space, it'll take more time. How many actions it can take your action space, that can also increase the time. If it only takes 2 actions, there's only like 4 total states it can be in, the time to train it's going to be much faster than if you have a continuing action space, right? Where it can move to a specific location, but there's like a million small different locations, right? If you think it can be off like 1 millimeter and then it can be off like 1.5 millimeters, there's multiple different positions it can be in, whether, if it's cutting, right? There's millions of positions, so then it might take longer. Yeah, that's another thing. A major issue, you can't train a real patient due to safety concerns, and that's what I said, right? So you'll use, and it's the same thing for self-driving cars, right? People don't necessarily want a self-driving car that doesn't know, correct? Because when they start off like a dog, they don't know what's going on, right? They'll just kind of be performing randomly. You probably don't want a self-driving car or a robot to just be starting off randomly in the real world, right? If you see a self-driving car, you want to be sure that it probably won't crash into you because it's just starting how to learn, right? If it's a dog peeing inside the house, it's not so bad. Sure, it's annoying, but no one's going to die because of it. A robot might happen, right? So you'll put it in this offline world where you can simulate all the events and there's no real consequences for it failing. And then here you can train it over time. And now I have this diagram here, right? So you have an agent, right? And it's in an environment. It's going to interpret its environment, right? It's going to get a certain state, and it might already have a reward for being in that state, for example. It's going to realize it's in that certain state. It's going to take an action, and the action is going to affect the environment that it's in, and then it might get a new state and a new reward based on the action that it took, right? So for the dog, right, in terms of the act, it can have like 2 actions, right? It can either pee or not pee, and it can be in 2 states, or it can be inside the house or outside the house. The same action can give it very different rewards depending on what state it's in. And so they work very much hand in hand, right? It'll pee inside the house. It'll observe what happened, which will be, I clean it up, I don't give him any attention. Okay. But then later on, it may realize, okay, took the same action, but in different state, which is peeing outside, and realized it did much better, right? It got treats, it got love, it got all this different affection. And then over time, it'll repeat this. And a very simple example could be the K-arm bandit problem. So K-arm, essentially in a bandit problem, you can think of it as a slot machine, right? Something they call the arm bandits, right? Because it has an arm that you pull. A lot of times, you're going to be losing money over it. K arm, it means you have K amount, right? You have some variable amount of different options. You have all these different slot machines you can choose from. And you want to choose a slot machine which is going to actually make you profit over the long term, right? And so now I have these 4 slot machines. So, which one do you want to choose, right? If you want to make money over the long term, right? If you had to guess right now, which one would you choose? You're probably just going to guess randomly. But over time, you may be taking down the overall average of how much money you make out of it, right? You take the expected value, and you may turn out that the first slot machine makes you overall in the long term makes you 30 cents. The second one makes you lose 40 cents. The third one makes you gain like 5 cents, and the last one gains you like 20 cents over the long term. And so you have these, right? You maybe run like 100 times on each one, and you realize these are like roughly the expected value you're at to get at these slot machines. And so your goal now is to make as much profit as you can. So you'll probably stick to this slot machine here, which makes you the most money. You'll definitely stay away from this one, which actually makes you lose money. And so that's essentially the K-arm bandit problem. How could you kind of apply? Oh, I don't know why it crashed again. Sorry about that. How would you apply this? Let's say you had a K-arm bandit drug trials. So you have this one singular patient and you want it to get better. And you have 3 different drugs, drug A, B, and C. So you're going to give patient A, you're going to give the patient the drug A, right? Because off the bat, you don't know which one's going to be doing the best. So you give it the first one and you get a +1 as a reward. Let's say he got better, right? And we represent it as some numerical value. So +1, it got better. Okay. Well, I still know how well the other 2 are doing. So I'm still going to try the other 2 at least once. So on the second run, I'm going to give it drug B and I'm going to see, oh, he actually did a little bit better than when he took drug A. That's very nice. But, drug C could still potentially be better. So I'm going to try drug C. I tried drug C. Oh, he actually did a little bit worse. His health kind of didn't do as well. And so now I have some sort of, I've only ran each once. And now I know, okay, drug A is like, give me a 1. Drug B will give me a 2. And then drug C will give me -1. Well, now if I'm trying to maximize his health, well, I'm going to give him drug B again. Okay, I give him drug B again. But now it turns out he actually didn't do so well. So he actually gets a -1. So now I'm thinking, okay, well, if I want him doing better, clearly drug B wasn't necessarily the best. It actually does just as well as drug A. So, okay, well, I'm going to try drug A. -1. So now drug A is overall like a 0. Drug B is overall a 1, and drug C is -1. Okay, well, drug B is still the best one overall, so I'm giving drug B. And now drug B gives him just no reward. He doesn't get better, but doesn't get worse. Okay, may want to try that again. -1, can have -1. So drug B is overall to -1. Drug A is overall -1. Drug C is also -1. No, sorry. Drug A is a 0, drug B is 0, and drug C is -1. So now drug A and drug B are kind of like pretty tied. So I may break the tie by choosing drug A, and they get a +1. And you may repeat this over and over. Now, does anybody see, a small, besides all the ethical problems, right, of just people, putting a patient on a bunch of different drugs back and forth, and obviously the medical effect that may take, right? We're assuming the scenario that the drugs being in a drug doesn't affect the next drug you're in, right? But does anybody see a problem that we had in terms of how we sampled things? If you don't see one, then you can say I didn't see a problem. This seemed just fine.
Drug C could be the best one, but we only tried it once.
Yes. So now you get into something called exploration versus exploitation. The first time I tried drug C, it didn't do so well, but turns out maybe if I sampled it one more time, I get like a reward of 100, right? But I never tried it, so I didn't know. Right. So you may, well, easy solution, right? I'll just explore more, right? I'll try drug C, drug A, and drug B more often, right? So I'll know which one's doing best overall. Okay, well, now you also have another problem. It's just like, if you know drug C is doing way better than the others, why are you still giving them drug A and drug B? Clearly you should clearly favor drug C now because it's doing the best. But now you have the problem, okay, well, yes, I'm going to favor drug C, but what if drug A and drug B over even longer term actually end up doing even better? And so there's no necessarily correct answer, right? Whether you want to go all in terms of exploration or all in terms of exploitation. It'll be a fine balance between the two. In terms of balance, it's not necessarily like a 50-50, right? Like I'll either want to, at a 50% probability, I want to explore, 50% probability, I want to exploit, right? Depending on the problem, it'll be a very specific ratio that will be like your optimal ratio. But still, it will be a very specific problem. And that happens into the more general, into like a more specific reinforcement learning problem, right? Where, my dog Galileo, he's peeing inside and outside the house, or he's not peeing inside or outside the house. The first couple times he does it, he doesn't really understand what's going on, right? But also he may notice that there's a fluke, right? A couple times I think he peed outside and I forgot to give him a treat. That's on me. But overall, it probably should still not affect him, right? He may still want to explore. Okay, well, does it actually matter whether I pee inside or outside? So he may decide to actually, pee a bit more inside. He knows that he really never gets any treats after that, and he pee a little bit more outside, and he realizes, okay, I really do get treats out of this. So then, hopefully, and I'm really hoping this is the case, which hopefully should be. Over the long term, he'll stop peeing inside the house. Eventually, a year in, you ask me how he's doing. I'll be telling you he's doing great. He doesn't pee inside the house anymore. I don't no longer have to clean up his pee inside the house. I really only have to pick up the poop when I'm outside walking him. And so that's a very, very big problem. There's still a lot of research going into, exploitation versus exploration. One thing you can say, right? If you're in the real world, you'll probably want to exploit more than you are exploring, right? If you have a self-driving, let's say you got yourself a Tesla, you probably want the car to be really exploiting all its knowledge that it can to perform the best action. Same thing with the surgery robot. You probably don't want the robot to start experimenting and exploring what it can do when it's performing surgery on you, or even a med student, right? You may not trust a med student as much as you trust a doctor with like 20 years of experience. Because the first person, they might still be trying out different things, or they're still learning. But same thing with the robot, right? It's still learning, and you may not want it to explore when it's doing that on you. But if you have this back into the simulated environment, you may want to have it explore way more, because there's no real consequences. There's no real world gain from it exploiting its knowledge. So you may want it to do a little bit more exploring. But even in that simulated environment, you still want to exploit, because you still want it to reach new states where when it explores there and when it exploits in those newer states, its overall rewards will be much greater than in all these previous initial states. And so there's a very, very fine balance, right? You're doing a lot of this, you'll be testing like where you're slightly changing some hyperparameters, but it is essentially running a bunch of simulations over and over again and seeing like how well is it doing overall, how fast is it learning, does it plateau very early on. And that is essentially the field of reinforcement learning. So back to bringing it over to supervised learning. Supervised learning, when we have these convolutional neural networks or whatnot, they're essentially just trying to map value A, like this value A, to a label value B, right? So they're mapping an X to an Y. They're nonlinear function approximators, which fancy terms essentially means I can map like any given value to any like other value, right? And the values don't have to change linearly. Doesn't really matter. You can map X to Y just fine. Reinforcement learning, it's not really just mapping a X to Y. It's taking actions and then receiving feedback on those actions and then performing your actions, where overall it wants to perform those better actions. And before I go on to the last slide, does anybody have any questions about either the Cannes-Bardet problems or reinforcement learning? No. All right. All right. So the final slides, as I promised I would give you puppy pictures. So here's my dog Galileo. This is like the first day that we got him. He's in a little blanket. There's another photo of him where he's deciding to play and like mostly sit on my face when I lie down. I wasn't so happy because then he kind of started to bite my hair, but he seemed to be very happy in the photo. So overall, if you have any questions, either do ask right now. You have any others later, you can. I am on the Slack, so you can message me on the AIM Slack. You can also always shoot me an email. And then you can also visit the Undergraduate AI Society on our website, uais.dev. And so we do have a couple of resources if you're trying to get into just more general machine learning. But yeah,